Welcome to this explainer. Okay, let's just get straight into it. We are strapping in for a really high-energy, totally efficient exam prep session today. We're covering assembly language and the little man computer, the LMC. Look, if you've been staring at a screen full of these weird three-digit codes and just feeling completely lost, well, you are in the exact right place. We're going to completely break down the key terminology, the core architecture, and really the fundamental logic you need to totally master your upcoming exam questions.
But before we get into the actual syntax and the code, I want you to think about this for a second. Are you ready to trace the journey of a single instruction through a computer's brain? Because today, we're not just going to sit here and memorize dry definitions. No way. We're going to take a spatial walkthrough of the CPU architecture. I want you to literally visualize exactly how data physically moves from memory to the processor and back again. It's going to be awesome.
So here's our game plan. 1. Assembly versus machine code. 2. Anatomy of the CPU. 3. The fetch, decode, execute cycle. 4. Programming with LMC. And 5. Our essential LMC exam checklist. Let's do this.
All right, section 1, assembly versus machine code. So picture this. The very first programming languages were just direct machine code. I mean, programmers literally had to sit there and enter combinations of ones and zeros, just ones and zeros. As you can imagine, programming like that was insanely difficult and honestly super prone to errors. I mean, one wrong digit and the whole thing crashes. So this pain pretty quickly led to the creation of assembly languages. Assembly stepped in and substituted those raw, unreadable binary codes with simple sequences of letters. We call these mnemonics, like add or sub. Now, it's still a low-level language, sure, but it is vastly more human-readable. It was a real game changer. But here's the catch, right? A computer's hardware still only speaks in ones and zeros. So how exactly do we bridge that gap? Well, we use an assembler. The assembler is basically a translator. It takes our low-level assembly language mnemonics and converts them directly into binary machine code. Listen, if there is literally one definition you need to lock into your memory for exam day, it's this one. The assembler is the unsung hero that actually makes our code executable by the hardware. Now, under exam conditions, you're usually going to be tested using the little man computer, or LMC. The LMC is what we call a reduced instruction set computer, or RISC, and it has just 11 simple commands. That's it. Real-world instruction sets and assembly code for actual massive hardware, they contain way more instructions. We're talking dozens of specialized registers, complex memory addressing modes, hardware interrupts, the whole shebang. But the LMC? It's the perfect scaled-down conceptual tool. It lets us learn the pure theory without getting bogged down by hundreds of different commands.
Okay, moving on to section 2, anatomy of the CPU.
Imagine the CPU as a little workshop. Inside this workshop, the absolute most critical area is the accumulator. You can think of the accumulator as the primary workbench. It's the specific register that stores the results of the very last operation or calculation. If you add a value, subtract a value, or just input a number, it lands right here, right on this workbench. And in the LMC, this accumulator can hold 3 digits plus a sign, which basically means it handles numbers anywhere from -9999 all the way up to +999. Next up on our tour is the program counter, or PC. So if the accumulator is our workbench, the program counter is the master to-do list. Its entire job, its only job, is to store the memory address of the very next instruction that needs to be processed. In our LMC simulator, memory locations only go from 00 to 99, so the program counter is only ever going to hold a 2-digit number. Think of it as a little pointer, just constantly directing traffic, saying, okay, go to box 5 next. Great, now go to box 6. And this whole setup brilliantly illustrates the von Neumann architecture. In von Neumann architecture, both your instructions, the commands telling the computer what to do, and your data, the actual numbers being calculated, they're all stored together in the exact same main memory. Our LMC simulator has 100 memory locations, numbered 00 to 99. But here's the slightly terrifying part. The computer hardware itself actually cannot tell the difference between an instruction and a piece of data just by looking at it. No way. It blindly trusts that the flow of your program is going to keep them separated. Pretty wild, right?
All right, let's hit section 3, the fetch, decode, execute cycle.
Let's actually trace the journey of our instruction. First up, step 1, fetch. The CPU looks at that program counter we just talked about, sees an address, goes over to that address in RAM and fetches the instruction. Then, step 2, decode. The CPU brings that instruction back and basically splits it up. In LMC, the first digit is the opcode. That's the action, like adding or inputting. The next 2 digits, that's the operand, which is just the address of the data we want to act upon. And finally, step 3, execute. The arithmetic logic unit, or ALU, steps up and actually performs the math or moves the data. Fetch, decode, execute. Over and over and over again.
Actually, let me break the fourth wall here for a second and give you a massive exam tip. Are you ready? You absolutely must remember exactly when the program counter updates. As each new instruction cycle begins, the program counter is incremented by 1, right at the start. This ensures that while the current instruction is being decoded and executed, the computer already knows exactly where to look for the next instruction when the cycle restarts. Don't forget that.
Okay, section 4, programming with LMC.
So one of the biggest points of confusion I see with students in LMC involves labels. Look, labels act as simple aliases. In LMC, we don't really have traditional variables like you might be used to in higher-level languages. Instead, we use labels. So, for example, if you tell the assembler to store an input into a label called first, the assembler might just assign that to memory location number 06. The machine code? It has no idea what first means. It only knows address 06. We use labels purely because they make the code vastly easier for us human programmers to read and follow. It just saves us a headache. Now, let's do a little active thinking here. Imagine you're running a program in the simulator. What visual state changes actually happen in the accumulator when we run an add operation? Like, how does the data physically flow onto our workbench? Let's walk through a concrete example. Say we want to add 10 and 4. First, you run an INP command, and the user types 10. Boom, that 10 appears instantly in the accumulator. We then use the STA command to store it away safely in memory. Next, we call INP again, and this time the user types 4, so the accumulator updates to 4. Finally, we run an ADD command targeting that memory address where we stored our 10. The CPU takes the 4 that's currently sitting on the workbench, fetches the 10 from memory, adds them together in the ALU, and bam! The accumulator instantly updates to show the brand new result, 14. And by the way, the sub operation works the exact same way. It simply takes the fetched memory value and subtracts it from whatever is sitting on the workbench. Oh, and here is a brilliant little coding shortcut for you. A lot of students think that right after they do a calculation, they have to use the STA command to store the result back into memory before they can output it to the screen. Actually, scratch that, you don't. Since the result of your ADD or SUB command is already sitting right there in the accumulator, you can just immediately use the out command to display it straight from the workbench. Skipping that completely unnecessary store command makes your code a bit faster and a whole lot more efficient. Which brings us to section 5, our essential LMC exam checklist. Let's lock this in. The absolutely crucial point here is knowing this core toolkit inside and out. You need INP to get user numbers and out to display them. STA stores your accumulator value securely into memory, while LDA pulls a value from memory right back into the accumulator. ADD and sub, they perform your basic math on whatever's currently active on the workbench. HLT completely stops the program. And finally, DAT. That is used at the very end of your code to reserve memory space for your labels. Literally, if you know these 8 commands, you are golden for the exam.
But we've got to watch out for the common pitfalls. These are the things that cost students easy marks on test day. Number 1, forgetting the HLT, or halt, command at the end of your logic. If you don't halt, the computer will just blindly keep trying to execute empty memory boxes. Number 2, improper label usage. Remember, the label name has to match exactly when you declare it and when you call it. And number 3, confusing data with instructions. Because of that von Neumann architecture we talked about, if you forget to use HLT, the processor will literally try to execute your stored data numbers as if they were operation codes, which will completely crash your program.
And just like that, we're at the end of our rapid review. We've covered everything from the assembler translating those mnemonics to the von Neumann architecture, right on through to writing and executing actual code. But before we wrap up this explainer, I want to leave you with one final thought. Now that you understand the fundamental logic of the LMC simulator, how will you apply this logic to master real-world assembly languages? Because the exact same principles of fetching, decoding, and executing, they are happening billions of times a second inside the device you are using right now. Pretty incredible, right? Keep exploring, keep questioning, and hey, good luck on that exam.